All right, I'll just get going. So hello, my name is Hagai. Welcome to Deep Learning for Developers, an introduction. So a bit about myself. I'm an engineering manager with Amazon AI based in Palo Alto, California. I'm leading a team that focuses on building deep learning tools and frameworks and systems for developers and scientists, folks like yourselves, so you'll be able to use deep learning and AI in your applications and services. So a bit about the agenda, things we're going to cover. We'll start by talking about why you should even care about deep learning, why it's a big deal, and also take you through a brief introduction to deep learning, talking just a bit about the theory. But then really this session is about an introduction for developers. So we're going to actually go through code examples, showing you guys what it is to actually code neural networks, deep learning models, and use them for inference in production. And lastly, Sungjae from Samsung will come on stage and talk to you about an example, real-world application of deep learning for cardiac arrhythmia detection, a project that he worked on in Samsung. So by the end of this talk, my personal goal is that you will be able to understand what deep learning is, what neural networks are, and how you can start using it today. Sounds like a plan? All right, cool. Then let's get started. So first of all, why it's a big deal? Why should you even care about deep learning, besides the fact that it's very much hyped? So I've quoted here Andrew Ng. Not sure if you've heard of him, but he's one of the really pioneers of deep learning for both research and application of deep learning. And he calls deep learning a superpower. So I'll just read his quote. "Deep learning is a superpower. With it, you can make computers see, synthesize novel art, translate language. If that isn't a superpower, I don't know what is." So that's a pretty bold statement. Let's actually try to see what it actually means. So if we take a step back, there is the broader field of AI, artificial intelligence, that was coined sometimes in the 50s. The questions that kind of started was, can machines think? But actually turns out it's actually pretty hard for us humans to even define what thinking is. And then Turing was one of the pioneers of computer science, maybe even the father of computer science, changed the context of the question to be, can machines do what we can, us humans? And he went on to invent the famous Turing test, which he identified as something that can test machines' true intelligence by merely imitating humans and being able to fool a human observer that the machine is really is a human or not. So artificial intelligence is really a broad field, somewhat philosophical, somewhat scientific. But then if we fast forward to the 80s and 90s, machine learning kicked in. And machine learning is really saw massive adoption, late 90s, early 2000s, and still today. And machine learning, much more specifically, it's a field that studies algorithms that are able to find patterns in data. So that's, subfield in AI, much more specific, much more applicable. And what's interesting about machine learning is it kind of changed the fundamental paradigm of programming. The programming that I have learned in school, and probably most of you as well, is one where there is the input data. The programmer composes some business rules through programming language, and then the machine executes these rules on the input data, and we get the answers, we get the results. Now, that's the traditional programming paradigm. Machine learning changes that. With machine learning, we provide the machine, the algorithm, with the input data. We also provide it with the ground truth, with answers. And the machine learning algorithm is able to identify rules that would match the data and the answers by itself. We no longer have to specify these rules ourselves. This is a massive paradigm shift, and it actually was really successful in solving a lot of different problems. Now, machine learning is really a basket of different techniques. Support vector machines, decision trees, logistic regressions, and there's quite a few others. One of these techniques is also neural networks. And that's the base for deep learning. Deep learning is really an advancement in neural networks. It's based on neural networks, and it's just yet one another machine learning technique. However, we have a whole session about it, and it's super hyped in the media. Lots of research paper going out every day about deep learning because of one simple fact, that it's able to solve problems much better than the other machine learning techniques, and the number of problems that deep learning is solving better than the other techniques is growing probably by the day. Okay, so let's move on to talk a bit more about why it's a big deal. So the first reason why deep learning is a big deal and why you should care is because it really has a growing impact on our lives. Now, if you just look at what Amazon does, the things that we at Amazon do, you can see deep learning in so many different applications. If you go to Amazon.com, lots of the personalization recommendation you see on the retail website are today based on deep learning. If you look at the back office of Amazon, you look at the logistical operations of Amazon, lots of the planning and execution in the warehouses and route planning is today powered by deep learning. Alexa and the voice revolution it introduced, so much of the capabilities of Alexa relies on deep learning, from speech synthesis to natural language understanding and more. And lastly, when you look at the space of autonomous vehicles, Amazon has the autonomous drones that are used for shipping merchandise. Lots of the capabilities of these devices is also based on deep learning. And of course, this also applies to the broader autonomous vehicle field with autonomous cars, etc. So that's just Amazon, right? And that list is much longer than what I'm showing here. But there's another reason for why it's a big deal, and that's that it's able to do better than not only other machine learning techniques, but also better than us humans. And I'll give you an example, kind of a classical example. There's a problem in computer vision called image classification. It's a problem that is pretty easy to define. Given an input image, identify the most prominent object in that image. And that was considered a very hard problem. And there was an annual competition for models, algorithms to solve this problem. And in 2012, Alex Krichevsky, a researcher from University of Toronto, with his team, was able to introduce a new algorithm, a new model, that improved the best algorithm to date by more than 30%, which was unheard of in terms of a leap in accuracy. And that model, as you may have guessed, was based on neural networks. And since that year, 2012, every year the winner of that competition was a model based on deep learning. And today, thanks to deep learning, this problem is mostly considered solved. But what's really interesting is not that only that these models do better than other machine learning techniques, it's also how it does compared to us humans. And this graph is taken from a study done in 2017, which compared the performance of image classification neural network, one of them ALEXNet, which is the model I just told you about, compared to humans. The blue dots over there are the algorithms. The red dot is human. So as you can see, there's almost 5% improvement that the models are able to show compared to the average human. And these models on the list, ALEXNet, GoogleNet, and VGG, they're not state of the art today. Today there are much better models for image classification. So going back to my original point, yes, deep learning is a big deal. There is a growing number of problems where deep learning is outperforming other machine learning models and even humans. And that's something we, as developers, as scientists, as builders, can and should leverage for our applications. Okay, and lastly, I want to show you just a cool example that I really like. There's really a big revolution coming shortly of autonomous vehicles. I don't know if it will come next year or 5 years from now, but everyone understands by now that it's coming, and it's really powered by deep learning. And this is a video by NVIDIA showing some of these deep learning models and how they power up autonomous vehicles. You can see the 3D bounding boxes around the other vehicles as identified in the camera. You can see it on both directions. That's one model that is used. And you can see another model for lane separator identification. All of these are pretty hard problems. It was very hard to get them right before the advancement in deep learning. This is another model for identifying safe driving zone. So you can see how the model correctly identifies the areas that are safe to drive. And you can see how it identifies the pedestrians. And this video goes on and on. It's, there's lots of similar videos showcasing the power of deep learning. You can just look it up. So hopefully by now you agree with me that deep learning is a big deal and you just want to grab it and use it. So let's go through a very brief introduction to deep learning. It's very brief. It's very hard to cover such a topic in the 30-something minutes we have. But hopefully it will give you the high-level understanding of the theoretical basis. So at the heart of neural networks are artificial neurons. They're inspired by the human brain, but it's very loose inspiration. And by the way, in our brain we have around 100 billion of these neurons and around 1 quadrillion synapses. That's extremely large, even in modern current terms of deep learning. So our brain is definitely something we can take pride of. But artificial neuron is actually much simpler. This is a diagram showcasing really the construct. And on the left side, we have x1 to xn. Those are the inputs to our network. You can think of it as a vector x with n entries. And then every input numeral value has an associated weight it is multiplied with. That's the entry to the neuron. The results of this multiplication, xi and wi, are then summed to produce one single numerical value, one single scalar. And that scalar then goes through a nonlinear activation function, which squashes the output to a smaller range, typically between 0 and 1. Now, the emphasis here is on the nonlinearity of that activation function, because that nonlinearity actually enables the neural network at large to model nonlinear problems, which, most hard problems are nonlinear. And then at the output of the neuron, we have a single value, y, and that's it. If you want a mathematical formula, that's it. It's pretty simple. You can implement it with 2 or 3 lines of code. And that's really at the heart of neural networks, okay? The wi to wn, the weights, are parameters that are learned during training, and we'll talk about that in a minute. But those parameters really represent the intelligence, if you will, of the network. Okay, now from that we take one step further and we talk about layers. Okay, so neural networks are really comprised of multiple layers that are usually stacked one on top of the other, but there are more complex models where layers don't have to be stacked, but just for simplicity and just to learn the basic concept, let's only focus on stacked layers. So you can see in this example we have 3 layers. The first one is usually termed as the input layer, and then we have the next one is the fully connected layer. Now, fully connected layer is a layer that is composed of multiple artificial neurons, also sometimes referred to as units, and those are the small circles. And each one of these units is interconnected to all of the neurons on the previous layer with these weights, wi to wn. And similarly, the next layer, which has multiple neurons, each neuron there is interconnected to all the neurons on the previous layer, and so on and so forth until we get to the last output layer. So that's the basic layer called the fully connected layer. Sometimes it's also referred to as a dense layer, and the name dense comes from the fact that if you look at all these lines, it looks pretty dense, right? So, and then the weights that I mentioned earlier, each one of these connections has an associated weight that is learned during training. We'll talk more about that, okay? Next, I want to talk to you about another type of layer called a convolution layer, right? That layer was introduced a bit later as neural networks started to gain steam. And this is a layer where there is it implements a convolution operator where you have a sliding window with a kernel, that's the matrix in the middle, that goes through the input array, or in this case, you can think of it as an image, and does pointwise multiplication and summation of the output. That's basically a convolution operation. And then that layer is able this way to take an input of two-dimensional or three-dimensional data. In this example, it's two-dimensional and output another two-dimensional output. The kernels, that's a small matrices in the middle that were in the example, those are the learned parameters of this specific layer. And again, they're learned during training. And this is an illustration of how these are learned, and every small square there is a separate kernel. And these convolution layers are really effective in recognizing patterns in visual data, such as images. It's very effective in other problems as well, including natural language understanding and signal processing. But I think if you think about this intuitively, the fact that you have a square and that the operation is operating on an area in an image kind of makes sense that it will be good for handling image data, because images have spatial information where close pixels have some kind of relationship with one another. To illustrate better how this works, when you combine a convolution layer across multiple layers, then the convolution is able to learn hierarchical features, with every feature learning more abstract representation of the information. So in this illustration here, what you see is the input image patches that generate the highest activation from their kernels, meaning these are patches that the neural network found interesting or thought had important information. So on the first layer, you can see most of these patches are just areas on the image where you have edges. And edges are usually fast change in pixel intensity or pixel color values. The next layer knows actually how to combine these edges into more complex or abstract entities, in this case, curves or corners, right? And if you go on forward, the last layer, layer N, is actually able to move to a level of abstraction where we actually see that what's the parts of the image that the neural network finds interesting are actually the interesting area of the image. In this case, lots of cat faces or dog faces. So hopefully this gives you the intuition for conv layers. And then lastly, I want to talk about another important type of layer, which is called recurrent neural network layer, or RNN for short. For some problems, if we take a step back from image processing into more signal processing, time series analysis, natural language processing, in this type of problem, predicting a given point in time, a given value, really depends on the context of things that happened before it. If you think about natural language processing, the meaning of the word at the end of the sentence usually really depends on the words that preceded it. And the same word can have multiple contexts, but if you read it in the right context, as human, we understand the right semantic of the word. And that's what RNNs help with. RNN layer remembers the past using simply just loops. So if on the previous artificial neuron we reviewed, there was an input X, and then there was some dot product of vectors, the weight and the inputs, and an activation function, and then we got the output Y. With an RNN, there is an internal loop where some of the data used during the computation is actually used also for the next time we compute the value. And this simple trick is actually super effective, proven to be super effective at problems of natural language processing and time series analysis. And this diagram kind of illustrates better what these loops mean. So if we take our input vector X and we kind of spread it, we unroll it, usually the term is unroll, in time, then the artificial neuron, the first one, works on the input X0, creates an output. Here we call it H0 and not Y, because H represents the hidden state. And that output H0 is actually fed in as an input to the processing of X1. Right? So the input for processing X1 is both X1, but also it's H0, the output of the previous input processing. And so on and so forth to the next unit and the next unit until the last unit actually has accumulated and processed the inputs from all the previous layers. That's how RNNs are able to remember the past. So, there are more layers. I won't go into more details, but these are really important layers to understand. And neural network are really multiple layers combined together, stacked together, they form a neural network. And the flow of data is sequentially through these layers. Typically, the first layer is called the input layer. The last layer is the output layer, where we get the output from. And then all the layers in the middle are called hidden layers. And they're called hidden because they don't interact with the outside world. They just get their inputs from their previous layer, and then they provide the output to the next layer. And by the way, the name deep learning, which was coined for neural networks, modern neural networks, comes from the fact that really successful modern neural networks have a lot of these layers. And so the term deep refers to the fact that they're very deep in terms of how many layers they have. So that's where deep learning comes from. So a few things that are special about neural network to summarize. First of all, they're nonlinear, thanks to the nonlinear activation function we mentioned. And that's super important because that's what enables them to model hard problems. Secondly, they demonstrate hierarchical feature learning. And just remember the example I showed of the convolutional layers and how each layer learns a new layer of a new abstract representation of the data. It goes the same to the other types of layer. Each layer processes information at a given level of abstraction and abstracts it out to the next layer. Another thing that is interesting and unique with a neural network is that the architecture is scalable, meaning you can always add more layers to represent a more complex problem. Similarly, you can remove layers to handle problems that are less complex and don't require so much expression capability of the network or too long training time. You can also augment the number of units you have in each layer. You have a basic architecture blueprint that you can play around with to scale for your problem at hand. And lastly, neural networks are super computationally intensive. And that's why we see how GPUs are so useful for neural network, but that's maybe a topic to another presentation. But just to give you an example, ResNet 152 used to be, until maybe 2 years ago, state-of-the-art model for image classification. It's called ResNet 152 because it has 152 layers, right? That's how deep it is. Just one single forward pass, through that network, taking an input, an image, and computing the output requires billions of floating point operations for just one. So that's how computationally intensive neural network can get. And we'll talk a bit more about the training process, which is even more computationally intensive. But that's what, one interesting property of neural networks, and definitely something you guys need to understand. OK, training neural networks. So I'm going to give you a high-level description of the training process. It gets much more complex than that, but I think you should get a high-level understanding. So we first do the forward pass. We take the input data, we feed it through the neural network, we compute the output of all the layers in a cascading fashion until we get the output. Once we get the output, we then compare the output to the ground truth output. And remember, when training neural network, and that's true for most machine learning or supervised learning algorithms, you need training data that is labeled. Just the input data is not enough. You need the input data and the ground truth for it. And then once you have the output, you compute the loss. And loss is kind of the difference between what the network said is the prediction or is the result and what the ground truth was. And there are different loss functions you can use. But all of them produce some kind of a loss. All of them should be differentiable. And then with that loss, we backpropagate it to the network. And backpropagation means basically we compute the derivative of the loss function across all the layers. And in every layer, we capture the extent of the gradient, but also the direction of the gradient. And once we have that, we go back and we update the weights just a bit in a direction that is opposite to the direction of the gradient. Now, what this trick gives us, it allows us to improve our model just slightly in the right direction. And then guess what? We just repeat. We repeat this process hundreds, thousands, tens of thousands of times, sometimes even more. And every step, we improve our model just a bit. And at some point, hopefully, we get to a spot where the accuracy of the model, the performance of the model is good enough for us to say, OK, that's enough. We can stop the training process. That's how training works. The forward-backward repeats across multiple epochs is really what allows the network to learn the correct weights. An epoch, by the way, is a name describing going through the entire training data set once. And most neural networks, when you train them, you need to go through your entire data set tens or hundreds of times. So you do tens or hundreds of epochs. And again, that's very computationally intensive. Training modern networks, even on GPU, a lot of time. All right, so that was the high-level overview. I want to show you some code and how you can get started with it. All right? So first step, set up your dev environment. You should pick a framework and go with it. Now, there's really lots of awesome frameworks out there. There is MXNet, which my team contributes a lot to. There's TensorFlow, there's PyTorch, there's Keras. Lots of other good frameworks. They're all pretty similar in the basic functionality. They allow you to build networks, to train them. They handle all the heavy lifting for you, like calculating gradients, not something you want to do necessarily. Doing the backward pass, implementing convolution operator, lots of pretty complex, low-level things that these frameworks do for you. So definitely you want a framework. Installing them is really easy. Most of these frameworks have really good API for training in Python. We'll talk about other language APIs shortly, but so with the Python package index, you just do pip install MXNet, and within a couple of minutes, you have MXNet and all of its dependencies installed on your local dev box or your cloud instance. And you also have the option to use a pre-configured AWS platform. SageMaker, if you've heard of it, is a great platform for doing machine learning and deep learning. It abstracts a lot of the complexity and infrastructure task for you. So I would highly recommend checking it out. There's also lots of great talks on SageMaker in reInvent. And you also have the AWS Deep Learning AMI. It's an AMI, a machine image for EC2 that comes pre-installed with all the frameworks, all the drivers, GPU, CPU, whatnot. And it's super performant. So definitely check it out as well. So I'm going to show you how to build a neural network now from code. We'll build a network called LeNet. It's a simple convolutional network, ConvNet for short, for handwritten digit classification. It was introduced by Yann LeCun. He's one of the pioneers of deep learning research. It was introduced back in 1998. So in terms of deep learning, it's really ancient history, but it's a great example. And it's not very deep. It has 7 layers. The first one is convolution, followed by max pooling. I did not explain max pooling, but it's a very simple layer that just downsamples the data processed. Another convolution with max pooling, and then 3 fully connected layers. And then if you take an input, in this case, it would be a 2-dimensional matrix representing a grayscale image. You feed it forward, and then you get a vector of size 10, an array of size 10, and every entry in that vector will have the likelihood of the index of that entry being the digit. In this case, we can see that the highest value is on the first index, the 0th index, and in this case, the network correctly predicted, right, the true digit that was provided as input. OK, so code. All of the code examples will be using MXNet, because that's what I know best, and that's what my team works on. But you can find similar examples for other frameworks. So with MXNet, you can implement LeNet with just a few lines of code. Let's briefly go through what we have here. So first of all, we import the Gluon NN API. Gluon is the name of MXNet's Python API. We move on to initialize a sequential network. And this is a sequential because we just stack the layers one after the other. And then we just stack them. We do a net.add, and we just call the initializers for the different layers, conv2d, max pool, another conv2d, another max pool, and then we flatten. Flatten is a layer that just takes the output of the previous layer, which in this case will be 3-dimensional, and squashes it into a 1-dimensional vector. And then a dense layer, which is the fully connected layer, another dense, and then the final dense, which has 10 output units, each one representing the output of the digit that we saw earlier. And that's it. With these lines of code, you have built your first neural network. Notice how MXNet really abstracts away all of the complexities. You don't need to even understand how convolution works. You just use that layer, similarly to other layers that are available. Now let's look at training, right? Training is super important. So again, with MXNet, it's pretty trivial to write the training code because a lot of the heavy lifting is handled for you. So the first line of the code initialize the loss function. In this case, it's softmax cross entropy. It's a pretty standard loss function for handling such classification problems. And again, MXNet has a built-in loss function for that for you. You don't have to worry about the implementation details. We initialize a trainer object, giving it the parameters and other arguments. And then we have a loop to iterate over epochs. Within each epoch, we iterate over our labeled data. So X is the input, Y is the ground truth output. We move on to do a feed forward. A net on X is really just doing a feed forward to the network. We get back the network prediction, which is Y hat. We calculate the loss function. We do a backward pass very easily just by calling .backward, which does the heavy lifting of backpropagating the loss and calculating the gradient. And then we call trainer.step, basically asking our trainer object, please update the weights so we take it one step forward in the right direction. And that's it. That's how you train. So training, can get complex and hairy, right? If you go, if you sidestep the kind of standard architectures. So many times you just want to grab a pre-trained model that maybe, your colleague or your data science team in the company created, or maybe there's a good model that is just available on the internet or on different model zoos. And that's really useful. It saves a lot of time. And there are different ways to use that. So one way is to just use the model as is, right? Maybe you want to be able to classify objects in images, and the standard classification models work for you, then that's great. You just use it as is. Another use case is that you want to fine-tune it with your own data. And again, if you go to the image classification example, you might want to be able to identify different kinds of flowers or butterflies. And then you want to take the image classification model and then fine-tune it on your own data. The good thing about it is that it requires much less data than training the original network. So that's a really useful use case. And then there's also transfer learning. It's a bit more advanced, but it's using the entire network or part of a trained network for extracting features. We won't go into the last two in this talk, but I'm going to show you a code example of how you use a model as is. So with the Gluon model zoo, it's pretty straightforward. Gluon or MXNet has a model zoo with multiple models. So you just import that vision model zoo, and then you just do a vision dot, in this case, ResNet 18. That's the model we want to use. It's an image classification model. And we get back the model with all the weights trained. So that's pretty awesome. And then to use it, just call model on your input on X, and you get a prediction. So it's as simple as that. There's lots of other useful models in MXNet model zoo for both vision, for natural language processing, and for other things. So I encourage you to check it out. Once you have a trained model that solves a business problem or helps with a business problem, the next thing you want to do is you want to deploy it. So you can use it for your service, your application, in production. And there are really lots of different ways to do that. You can use SageMaker, which allows you to host models with just one click or one API call. It's pretty cool. If you want to deploy to an IoT device, you can use AWS Greengrass or similar platforms. You can also use just EC2 instances, which come pre-installed with model serving capabilities like TensorFlow serving or MXNet model server. You can use containers, or you can write your own solution. Writing your own solution for inference allows you to actually break free from Python, right? I mean, I know that most of the production systems out there, or many of them, are not based on Python. They're based on more standard stacks like Java, like C++, C#, and whatnot. MXNet and other frameworks has good inference APIs for all these stacks, like Java as well. And I want to show you an example of a Java, the MXNet Java API. which allows you to do inference from Java. So in this code here, we first initialize the context, asking inference to run, in this case, on the CPU. We can also change it to be on the GPU if you'd like. We move on to define the input descriptor. That tells our inference engine what kind of input the network handles. And then we initialize a predictor object, giving it the path to the model to load the model from file. And then we just pre-process the input image, and then we just call predictor.predict. And that's it. We get a Java float array as a result with the prediction results. And you have similar APIs for C++, for example, Scala, and other popular languages. So that's pretty cool. OK, so we're done with kind of looking into some code examples. I want to encourage you to get started with deep learning. I showed you these applications we're using within Amazon, or some of the applications we're using with, deep learning within Amazon. But really, there's so many other exciting applications where deep learning can really solve problems that were very hard to solve so far in healthcare, in finance, in cybersecurity, in robotics. And these are just a few examples. There's so much more. There's great resources available on the internet. You can just go ahead out. Most of the code example I've shown were taken from the Gluon crash course. The link is over there. It's like a 1 hour, 2 hours crash course that you can go through. And there's also MXNet.io website. SageMaker has great documentation. And beyond that, there's great resources on the internet out there that allows you to get started as a developer, get started with deep learning. All right. I want to invite Sungjae to stage to talk about deep learning application for cardiac arrhythmia.
Thank you, Hage. I'm Sungjae Min. I'll talk about cardiac arrhythmia detection with deep learning. Let's first talk about what is cardiac arrhythmia, also known as heart arrhythmia. It's a group of conditions in which the heartbeats are irregular, too fast, or too slow. In more detail, let's look at the top left graph here. As you can see there, there's electrical activity which is recorded using electrodes that are placed on your skin. And it is called ECG, also, or EKG. And the top right graph illustrates the schematic diagram of the normal heartbeats that are seen on this ECG graph. It consists of a P wave followed by QRS complex, where the R indicates the peak pulse. And then there's a T wave there. At the bottom, this is we screen captured that we are monitoring the ECG graph here. Now, why we need AI in cardiac arrhythmia detection? So let's look at the challenges here. Every year, over 300 million ECGs are recorded, and each ECG, which is usually a 24-hour recording per person, usually has more than 80,000 beats, heartbeats. This is a huge data. And it usually takes a lot of effort by the expert clinicians and cardiologists because they have to examine this ECG data. And the fact is that if a person has the arrhythmia, usually only 2.5% of the heartbeats will have irregular patterns. And all others, like 97.5% of the heartbeats will look normal. So therefore, if AI can mark these irregular patterns, and then these clinicians and cardiologists can only focus on those marked heartbeats, it will dramatically save the clinicians and cardiologists' time. And also, it will increase the accuracy of the diagnosis. So that's why we want to apply in cardiac arrhythmia detection. So then what is the challenges for the traditional machine learning? In other words, why we apply deep learning instead of traditional machine learning here. So there are at least 40 different types of arrhythmia. The top one shows the ventricular tachycardia, which is marked as V in each heartbeat, and N for the normal heartbeat. And at the bottom, you can see the atrial fibrillation, which is also called AFib. You can see that there's the intervals between the heartbeats are irregular. We call this one AFib. And you can tell them that there are various types of arrhythmias, but it is difficult to describe them in words. What are the main features of these different types of arrhythmias? So one good thing about deep learning is that deep learning has the capability called automatic feature extraction. So you provide this data with labeled data, then deep learning will do the automatic feature extraction for you. If you're using machine learning, then you have to do it by yourself. You have to find out what are the features that's differentiating these different types of, 40 different types of arrhythmias. So that's why we are using deep learning. Also, the second reason is that each person has her own normal beat patterns. So top one is called inverted T. So usually T wave has the positive amplitude, as you can see on the left figure. But the top figure, this person has a negative amplitude. But for this person, this is a normal heartbeat. Maybe this is caused by the fact that he might have a hyperkalemia, but this is his normal beat. The bottom one shows the large T case. Large T means that usually the R peak should be the peak one. But in this case, this person, the T wave is higher than the R peak. Also, for this one is his normal case too. So what it means is that when we train this arrhythmia case, the normal type, normal heartbeat, there are so many variations. So, which means that there are many input data for training. And usually when you increase the data size for training, the performance of accuracy will go up too, proportionally. But it will reach a saturation point at some point. So no matter how much you train input data, the performance will not increase. Researchers are saying that the difference between machine learning, traditional machine learning, and deep learning is that deep learning will reach this saturation point much later than the machine learning. So you can put more input data for training. So, and this is the case. Cardiac arrhythmia has a lot of input data to train. So that's one of the reasons why you choose deep learning for this one. Now I'm going to talk about how we apply deep learning in cardiac arrhythmia detection. The first step is pre-processing. You can see in the gray figure that that's the ECG. It's a time series data, and we apply time window and apply the FFT, which is a fast Fourier transform. FFT will translate the time series data into a frequency data. And then as we move this time window, slide this window to the right, we get the time frequency information, and each consecutive frequency information will be appended to each other. Then in the middle, we will get the frequency domain data in a two-dimensional fashion. Then we fed this two-dimensional image data into the CNN, convolutional neural network, as Hage explained. This CNN will extract the features for you. So I'm showing the four most representative features here. And these features, the output of the CNN. And these features, will be fed into the RNN, the recurrent neural network. So RNN will do the classification for you. The output of the RNN will be 40 different types of arrhythmia. The input here, which is a 90-degree clockwise rotated input, This input from top to bottom as the time increases, fed to the RNN as a x1, x2 to the xn. And within RNN, there's a forward direction indicated as a blue node, and there's a red one that's for the backward. The reason why we have forward and backward is because we want to capture the relationship between the current heartbeats and the previous heartbeats, and also the current heartbeats to the next heartbeats. So in order to capture that relationship, we use the both bidirectional RNN. So once you train the model, how you deploy this one? There could be multiple ways to do that. I'm showing one example here. Here, the patch that senses the ECG data is placed on the skin near your heart. And the sensor data will be stored in your mobile device, for example, your mobile phone. And depending on the setup, and once your mobile device has a Wi-Fi access, it will upload the data to the cloud. And inside the cloud server, it will perform the analysis. And the result will be sent to the hospital so that the doctors in the hospital can see this result. This screenshot image is from our tool, shows the ECG diagram. And you can see that some of the heartbeats are marked as red so that the doctors can only examine those marked heartbeats, which will greatly reduce the time for diagnosis. What are the use cases for here? It ranges from first responder monitoring, elderly care, to sports performance tracking. Now, I'm going to talk more about optimization phase. So building a model is easy. It's usually the optimization phase that takes time. So we first focused on the accuracy. And then we found that once we trained it, when you run it on GPU, it took about 20 minutes to process 24-hour data, ECG data. We call it inference time here. Since we wanted to reduce the cost, we changed from 4 GPUs to 1 GPU. It became for 80 minutes. And then we replaced the GPU with CPU because CPU is relatively cheaper than GPU. And then it became 120 minutes, which is almost 2 hours, which is 2 hours. And we wanted to, our optimization goal was to reduce this inference time. And also, we didn't want to sacrifice the target performance, the accuracy. So that was the goal of our optimization. And this graph shows our journey about how we achieved our target goal here. So there are 2 graphs. Blue one is the latency. So it started from 120 minutes, 2 hours. And after multiple optimization stages, at the end, we achieved within 3 months, 3 minutes, sorry. 3 minutes to process 24 hours data. So the lower, the better, because it's the latency. And the red graph is the accuracy. So we start the starting point is 100%. And then if you optimize for speed, then performance may drop, it may degrade. And later, we also apply the optimization for the accuracy, so that we can go back to the 100%. Let me go through a little bit. So the leftmost column, we started from 16 CPUs. The algorithm used was a bidirectional GRU, and sampling rate was 256 Hertz. So in order to reduce the latency, we first reduced the sampling rate from 256 to 128. Then the latency is reduced. And also the accuracy dropped. So that's not what we wanted to do. So the next stage, We also reduced the number of CPUs, but also we applied MKL, which is a math kernel library from Intel. And then it canceled out each other, so the performance for speed and accuracy remained the same. And then next, we changed the algorithm, and it reduced the number of operations and so on. So at the end, we achieved 3 minutes with the same accuracy performance. So usually, this is the process that you do when you apply the optimization technique when you do the deep learning model. And the last one is as a future work. This is our we are currently building this tool called Brightix Studio. Usually, when you perform deep learning with deep learning frameworks, such as TensorFlow, MXNet, or SageMaker, you need to be familiar with some Python coding. But here, for those of you who doesn't want to do any Python coding, we are providing some visual programming environment here that, for example, in the top left node with the purple one, in that setup stage, you can specify what region of you can deploy your Amazon instance. So, for example, you can specify whether it's the east coast of the US or west coast of the US. And then you do the modeling. And then you send your model to the SageMaker, and SageMaker will do the optimization for you, and SageMaker will return the result. So this way, you can interface with the SageMaker. And this Brightix Studio is an open source tool. We open sourced it this month. And current release includes the interface with the machine learning. And this interface to the deep learning frameworks will be released early next year. And that's it for my talk. Back to you, Hage. Thank you.
Good job. Thanks, Sanjay. So we wanted to thank you guys. We actually have a meet and greet session, so you can come meet us in person, talk to us about your deep learning questions, discussions of what can you do with it. It's on ARIA East, level 1, the Willow Lounge. We'll be there. It starts 15 minutes from now. And yeah, we'd love to see you guys there and touch base and get to know you and your use case more. And lastly, I was asked to remind you guys, don't forget to complete the session survey in your mobile apps. Thank you.